if you guys could tell me if they have sound. All right, it seems like it might be working now. Okay. So for those that are just joining us because you didn't have sound, I apologize. We're just talking about the exam, a sheet of notes, front and back, handwritten. Can be done digitally, but it needs to be handwritten for exam 1, which will be on the 24th of February. Any other questions? Yes? Right. iPad notes are fine, but they need to be printed on a sheet, right? And a front and back. That's fine. And, you know, I was a student, and I did like this kind of almost micro handwriting, all right? So don't take it on the iPad and synthetically make it smaller, all right? Does that make sense? You know what I'm getting at? All right, within reason, okay? I don't know, I don't want to be like really, you know, I just want it to be fun. It's going to be conceptual, okay? The exam is going to be conceptual. If you see from the past exams, it's based on being able to apply the different formulas. Essentially, though, you're going to have maybe 10 formulas. You write down the 10 formulas and you know how to apply them in different orders and different ways. You're going to be, that's going to be the name of the game, okay? But don't randomly apply them. That doesn't go very well, of course, okay? It's like, oh, there's a pressure, there's a force, oh, I'll just put it in this equation. You're like, no, that's not the right one, okay? I'm sorry, it's going to be tough, all right? It's going to be tough, so please spend some time studying, all right? It's going to be tough. Okay, so let's go ahead. Oh, can people online hear us now? They're good? All right, great. So today we'll do a brief review of what we covered last time in session 4. And then we'll get into material properties. We're going to spend a couple of sessions discussing material properties and how we connect them to problems that involve loads and bars, essentially, at this point in the game. The last time we met, we talked about stress and strain, and we introduced some jargon. So if you want to sound cool on a Friday night, you can talk about the traction vector, right? It's like, oh, the traction vector. What is a traction vector? Well, it's a construct that we have with 3 components for stress, and it allows us to understand the behavior the material is experiencing. It kind of has feelings. No, it doesn't have feelings, but it is the construct that we use, okay, to take a resultant force coming out of a given plane or surface and be able to describe 2 sets of shear stresses, or 2 shear stresses, and 1 normal stress on a given surface, okay? And then we talked about how we can have essentially 6 components, or if you have the tensor, 9 components, but really you have 6 components for our intents and purposes in this class, where we have 3 normal stresses, sigma x, sigma y, sigma z, and we have tau xy, tau xz, and tau yz, okay? And with those stresses, we're able to describe, or with those vectors that have scalar form, also positive, negative sign, right? We're able to describe the state of stress at a given point. Then we talked about strain associated with axial loading. We talked about shear stress in a little bit more detail and shear strain. And we will get back to talking a lot more about shear stress and shear strain in a little bit. Okay, but first, we're focusing mostly on normal stress at this point and normal strain in bars. Okay. So, oh yeah, and that was the shear one. All right, so has anyone done any tensile testing, material testing? Yeah?
Whoa.
Yeah, what? Do you want to talk about it? You don't have to, but what? Okay. An impact test, like a Sharpie?
It's mostly compressive. It's like a metal. Yeah.
Oh, okay.
It's there to like absorb.
Okay. All right, cool. All right, so you're measuring in some way, shape, or form how much energy the material is able to absorb and get an idea of whether or not it's going to fail when you apply that much energy. Is that what you were going to say too?
No, we also do another thing. That is for RFR.
Right.
But we also certify our welders using the Indeterminate, and that's a tensile test. So we have dog bones similar to those,
Okay.
and we cut them and have our welders weld onto them, so that we can see like if the material fails at their weld or if the material fails just using material properties.
Okay, great. So do you have like a jig that you put them in to test them, or you kind of just
No.
use a hammer and you're like, this is not going to work?
We use an inchtron.
Okay.
I don't know who. I think Measurements Lab might have it.
Okay, yeah.
Somewhere in the somewhere in the MAE building, there's an inchtron.
Yes. Yes. I'm guessing it's in Pellegrini's lab, but yes. Okay. Good. 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 All right. Great. So you have some familiarity with what some people have some familiarity with what material testing looks like. And if anyone's ever broken a rubber band or twisted the paper clip, you have some natural experience understanding how materials fail. And if you apply more load or more strain, there's a higher likelihood that you're going to cause some type of plastic deformation, yielding, or ultimate failure. What is the purpose of testing? Well, we want to characterize the intrinsic properties of the material so that we will know how the material will behave when we form it or place it in a structure. The last time we were here, I discussed briefly how you're not going to take a bridge and put it in a material testing machine. Although there are machines that allow you to do diagnostics on structures of large size, the idea is we take small pieces of material that are used in larger structures or vehicles or toys, whatever they might be, and we get an idea of how they're going to behave so that when we design, we can predict whether or not we're going to be exceeding the capacity or the strength of the materials that we're using. Or it could be that we're going to be able to understand how much deformation that we have and assure ourselves that we're not going to have a sagging bridge or something that's going to deflect beyond what we would like. We often use coupons or test samples like you see in this diagram or you see here, and they can be cylindrical, they could have threads on the ends, or they could be flat-like or squarish and have areas on which you can apply some big jaws or clamps. Or it could be a compression test where you essentially have two flat surfaces and you put it between two platens and you push those platens together to be able to generate some compressive stresses. Okay? So this is what the testing apparatus looks like. Any idea why it's wider here and here than it is in here? So it fails in the middle. Why would it fail in the middle and not at the outside? Right, it's thinner, right? And so we have an idea based on our discussion of stress, right, that the stress is going to be dependent on the cross-sectional area. So we want to have larger regions where you're gripping so that the failure happens in the middle. Now, is it going to happen here, 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 or here? I don't know. You don't really know. You just want it to happen in a region. But there's some randomness to this. And where the defects may be or may not be, that's where you would expect or not expect there to be failure. And there are specifications. ASTM has standards on these, for example, and suggestions in terms of what the radius should be here and here and here to avoid having a mishap or avoid having a test not fail or avoid having a test fail where you don't want it to fail. Okay? As we discussed last time, we're able to calculate stress based on a normal force and an area, and we were able to relate an average normal stress to an average normal strain. So we don't say, well, at this point it's going to be exactly the same as that point, is exactly the same as that point, right? We don't, it's hard to make that prediction, but for many intents and purposes, we can say, hey, look, the average is going to be about right. It's going to be about the same across the cross section. And typically, you or I or we would control the rate of extension and monitor force and keep that rate of extension constant. So what does that mean? That means that we're going to be saying, hey, go 1 millimeter a minute, okay? Something like that, whatever it might be, okay? And that might be a lot, okay? Maybe we only want to go 100 microns a minute, whatever it is, within some resolution of the machine. We're going to apply that displacement, and we're going to measure the amount of extension either optically or with contact extensometers, that are called, right? Real original name, extension extensometer. And we also need to measure the force, okay, with a load cell. Turns out these big machines, you see that these machines have some size to them, okay, here and here. Okay. So like, let's see, do I have another machine? Okay, maybe that's all, those are all the machines I showed. Those machines are pretty large, and they need to be able to handle high loads in some cases, but with their size, they have also the ability to flex or stretch some. And so what you want to do for more accurate measurements, or measurements with high accuracy, is have the extensometer either contacting the sample directly, or you have a camera that's looking at the sample directly and you're measuring the distance between 2 points on that sample. Or you do something called digital image correlation, where they have like a bunch of speckles on the sample, and they have these complex computer algorithms that are able to calculate strain from the images based on the fact that all these dots are moving really small amounts. And then the load cell, that's what measures the force. Okay? And so that's going to be in series with the sample. As we know, we put springs in series with each other, the force is going to be the same. Any questions on this? Okay. So when we perform these tests, typically for metals, where we have, or alloys where we have small strains for a given amount of stress, we use what's called the engineering stress. And the engineering stress is based off the original cross-section. We'll call that A naught. So you have some force and it's scaling up, but we're going to assume that the cross-sectional area is more or less staying constant. As we'll discuss on Friday, not true, but again, it's typically pretty small for the types of displacements and strains we're discussing, so it's not bad. If you're using a rubber band or something that's rubbery, then you're probably going to want to use other methods of measuring the cross-sectional area to get a true stress. So the engineering strain is essentially, engineering stress is just this force divided by the initial cross-sectional area. The nominal or engineering strain is going to be based on the original length. So we're going to measure that length and then say, what is the little delta? And that little delta divided by L naught is going to give us the strain. Again, there are other ways of calculating strain, and this is typically good enough for this class, for what we're going to be discussing. You try hard to set up these experiments, and be very careful with the instrumentation, have a great load cell, have a great extensometer. What does that mean? What does great mean? Well, it means that the level of noise you have is low compared to the minimum amount that you're going to measure, right? So someone says, hey, I've got a 5 kilonewton load cell. Do you want to use it? And you're like, my sample is really small. Small cross-sectional area, has a low elastic modulus. I only need 100 newtons of force, max. Well, let's just imagine that both the 100 newton load cell and the 5 kilonewton cell have a range between 0 and 10 volts for their output. Okay? So that means that the 100 newton load cell, right, you're going to have 10 newtons per volt. Okay? Whereas the 5 kilonewton load cell, right, that's 5,000 newtons over 10 volts. That's 500 volts, or 500 newtons per volt. Okay? And let's just say that there's noise in that voltage signal. If you're trying to measure 3 newtons, the 5 kilonewton load cell may just spit out noise that's going plus or minus 5, 10 newtons all the time. Okay? Whereas the 100 newton load cell would be able to give you a more stable readout and probably get you down to the 3 newtons. Does that make sense? So bigger is not always better, right? And accuracy and resolution and repeatability are all factors that go into being an experimentalist trying to do careful characterization of a material or a process. Temperature can also affect your measurements. We won't talk about temperature much in this class, at least from the perspective of, okay, how does the elastic modulus depend on it? Okay, we can talk about it a little bit with heat treatment and things of that nature, but when you take mechanics or material properties of materials, all right, they'll talk more about how the microstructure evolves and changes based on the quenching or the annealing processes that might be in place. But we're going to kind of just say, hey, here's your elastic modulus, have fun. And yes, little microdents or voids can end up leading to imperfections and issues with your tensile testing as well. Okay, any questions on this? Good? Fun? All right. So what do you get out of the machine? Well, we're going to go into more detail, okay, in terms of how you make a graph and how you calculate some of these values. But this is what you're looking for when you're interested in using a material in an engineering application. You're looking for a plot that has stress versus strain. Okay. So the units of stress, right, are force per area, and the units of strain are dimensionless. Okay. But maybe they say, oh, this is going to be a microstrain, right? We discussed this last time. Maybe this is going to be in percent. Okay, but it's dimensionless. Now, one point on this stress-strain curve could be the proportional limit. Okay? And there are going to be a few values here at the beginning that are almost right on top of each other, and so often we don't distinguish them. But the proportional limit is saying this is a point through which I can draw a line and I have a constant of proportionality. Okay? So I get to this point. After I get to this point, okay, it could be here. I mean, this is not super precise, right? But it could be here, it could be a little bit here, whatever, it could be down here. Okay? I start to go nonlinear, right? People like that term nonlinear, but you can see this is a line, this is something that's not a line. Okay? At least, you know, it has some other behavior. The elastic limit. Okay? Elastic limit could be a little bit higher, And the elastic limit is the stress to which you can go, and when you unload, you spring back all the way to 0. Okay? So this is a key point in design. We want to keep the stresses low enough so that when they are applied and when they are released, there is no resulting deformation. Does that always happen? No, okay, obviously. But that's kind of the typical goal for a design engineer. The yield stress or strength, okay? So this point right here, a little further up, given by sigma y or sy, is very similar to the elastic limit. And they could almost be on top of each other, all right? But the yield strength is, once you get to that yield strength, you will no longer go back to 0, okay? So there, again, the elastic limit, or the proportional limit, the elastic limit, and the yield strength are often just assumed to be at the same location for most intents and purposes. We'll discuss a little bit about how you might calculate a yield strength though later. The ultimate strength or ultimate stress, okay, out here is, as you guessed, the maximum stress that the material will handle. You don't want to be operating out here, usually, okay? And what you see is that the slope falls off and kind of becomes flat. Do you know what that means when it becomes flat? That means that if you keep applying the same amount of force, which is the same amount of stress, the material keeps straining. Okay, now there are situations where you have polymers that creep and different things of that nature, yes. But this, when you're dealing with the metallic alloys, this is a big time no-no. Okay, big time no-no. You wanna be down here. Unless you're trying to break it, okay? Maybe you have a system that you're designing where you want the user to be able to pop out their gum from a package, right? So you've got this really thin piece of metal there. So you actually designed it so that it does fail, okay? And that is not too hard to open. Or a bag, right? Some of you are probably packaging engineers, right? Do we have any packaging engineers? Okay, well, if you were a packaging engineer, you're breaking stuff, okay? And then the last one is the fracture stress, okay, sigma F. And this is where, yes, we've gone beyond necking, which we'll show a little bit in more detail. Probably more, actually I'll talk more about that, I guess, on Friday, if I have time. And that will, that's when you break, okay, that's when you rupture. That's it. Okay. So like necking, you can kind of see it here, all right? These samples, they had a cross-sectional area, then they kind of tapered out, they thinned, and then they broke. Okay, and there is a difference between a ductile material and a brittle material. And if you look at some of the videos I posted, I wish some of these videos existed when I was taking this class, because I think they do a better job explaining graphically the principles than I can with my hands or my voice, okay, or my drawings even. But a brittle material is a material like you see here. It just, and I guess that's something to be noted, right? When the curve ends, sometimes people put an X there. All right, that's it. The material has ruptured. It's broken. So brittle materials, they have typically kind of a more sudden catastrophic failure. They snap, right? Imagine glass, a ceramic, something of that nature, right? You throw a rock at it and it just shatters. Something metal, like the hood of your car, right? You throw a rock at it and it puts a big old dent in it, okay? That is an example of ductility. And so whoops. What you have here also, and we'll talk about this more next time, is an opportunity to measure the energy under these curves. Okay? And like you all were talking about your impact testing, I think. With the impact testing, you're going to be looking at this property here. Okay? How much energy it is able to absorb. Okay. So, some points that we already might have discussed too. It's often very difficult to distinguish between the proportional limit, that's this one, the elastic limit, and the yield stress or yield strength. Okay? There are two overall behaviors. One is what we call elastic behavior. So elastic means it springs back. Okay? It's in this linear regime. I had to watch what I'm doing. It's in this linear regime right here. And there's plastic behavior. Okay? And you have what we'll call setting or permanent strain. And I need to talk about that in a little bit too. So elastic region or regime is linear in its response, whereas the plastic region or plastic behavior has what we call yielding, okay, or strain hardening. Okay, so the material is actually getting harder, and I'll explain that a little bit in a little bit too when we start drawing some curves at the end of today. And you can also have necking, which we talked about here. And watch those videos. They do a really nice job of explaining a lot of these different mechanisms and behaviors. Now, for the next little bit, let's just focus on the elastic region. Okay, so that's that linear response region. And we're going to talk about a constant. Yes? Okay, this? Okay, so not all materials do this, but low carbon steel is one that shows a definitive yield point. And if you look online, you will find some very complicated explanations for this behavior. Like, why does it do this little pop? Okay? And they're jargon terms like pinning, sliding, gliding, okay? You get to a point, if you think about these atoms or molecules having their interatomic or intermolecular forces, where you kind of stretch things out and either dislocations or other things can kind of creep in, or things start to break and they slide, and it actually becomes easier temporarily for you to apply stress, or I'm sorry, a strain, okay, and it actually goes down. All right, but this is actually a pretty complicated phenomenon that we won't go into right now. Yeah, then it hardens. Yes, that is true. Okay, and so you can introduce what are called dislocations, and they kind of become like these hard knots. It's not wood, okay, but they become like these hard things in the structure that actually make the material stronger. Okay, and so this is one of the wonderful things about steel and some of these alloys, is that you're able to increase the strength of the material by purposely plastically deforming it. Okay, so like if you look at the Efficient Engineer video, the one where he talks at the very end, he talks about a sword. And so there are things they can do with heat treating, for example, to make the outer edges of the sword very hard. Okay, and like a blacksmith might be doing some stuff where they're pounding it and heating it. Okay, where the outer edges become very hard and sharp, essentially, but the center of the sword becomes, or it remains ductile, somewhat ductile, right? So it gives you the little flexibility. Okay, so metals are really cool. You started with the same material, but how you processed it is giving you different attributes at different locations. Okay, so we're in the elastic regime, okay, this linear regime. And we've talked about Hooke's law already in terms of F equals K delta. There's another form of Hooke's law, which this definitely goes on your formula sheet. There's a reason why it's so huge, okay? Sigma equals E epsilon. Now, what is E? E is the elastic modulus, okay? This is the elastic modulus, or the Young's modulus, okay? So, or Young's modulus. What is sigma? We already know what sigma is. Sigma is a stress, and these are normal stresses. And epsilon is the strain. So epsilon strain has dimensionless units. Stress has units of force per area, which means that the elastic modulus is going to have units of force per area. Please keep that in mind. So how do we determine an elastic modulus? I was in a meeting recently, and one of the faculty members was stating one of our students went to an interview recently, and they're asking in the interview, how do you calculate the elastic modulus? And she didn't tell me whether or not the student got it right, but apparently the other interviewees were kind of stressed about this question. Okay? And I remember when I was an undergrad, I was an undergrad, I had a friend who had been in an interview, and the guy that walked out right before he went into the interview said, I couldn't remember the difference between stress and strain. Okay? So these concepts are valuable not just because they're interesting, but you might actually need to know them for a job or some other opportunity in engineering. After that conversation, I thought, okay, and I'm like, oh boy, right? Who's been teaching mechanics and materials? Right? So let's make sure that we know how to calculate an elastic modulus. And here are some steps that we might follow. First, and I just wrote these down because, and you could add or subtract steps, okay? But this is kind of what came to my mind. First, go ahead and fabricate an article, a test article, right? You want to sound fancy. I'm going to use a test article. I'm going to make some samples. And you want them to have the same cross-sectional area, and you want them to have the same length. I didn't put this there, but you probably want to do more than one test, if possible, okay? Because you want to be able to calculate a standard deviation, you want to be able to calculate a mean, and get some idea of how uniform the material might be. Now, next, after I figure out, how it's going to fit in the machine and all that, I got the grips, I can clamp it real nice. We're going to specify a constant rate of extension or compression. Okay, so if it's a compressive test, all right, or if it's an extension test, and I put L per minute. That's actually probably not the greatest. Maybe it should be like length per time, just so that L is a length, time is a time, right? Or I could have said, something like millimeters per minute. I don't know, whatever. And that's going to be the machine pulling this apart, but you need some way either to measure the extension with a video or images, or with an extensometer. Or, to be honest, if you don't really care that much, you're not too concerned about the precision, and the machine's not too big, you just be like, I'm going to use what the machine tells me in terms of displacement and call it a day. All right. So it depends. It depends on the system, especially if you're doing things like with the polymers, where the extension is going to be quite large and the machine is quite stiff. Okay, relative to the polymer that you're testing. Yes, there's going to be some slop in either the gear train that's being used or in the hydraulics that are being used, but you might be able to get away with that. Then have a way to measure the force. Okay, so we got to measure the force while we're doing the test. And as we discussed a few seconds ago, the load cell is going to be in series with the sample, so it's going to be experiencing the same amount of force that the sample is experiencing. Then plot the force versus the displacement. Okay. Notice this is not a stress-strain curve yet. It is a force versus displacement curve. This is what the machine will be telling you, or your sensors and everything else. It's our responsibility to convert these forces to stresses and these displacements to strain. Okay? So sigma is equal to F over A, and strain is going to be the little L over the big L. And then, what do we do to figure out the elastic modulus? The elastic modulus, okay, is this slope in the linear region, right? We said that sigma is equal to E times epsilon. And that applies here. Any questions on this? So someone gives you a stress strain curve, you have an idea of what they did to get it now. And you can take out your handy dandy ruler, or you can do it by eye, and you say, okay, I can figure out the elastic modulus. Now, if this graph starts at 0, 0, if the line's going through 0, 0, does it matter which point you pick? Not really, right? As long as it's something below the elastic limit or the proportionality limit, okay? Or these guys are even going farther and saying that the true elastic limit is down here. Okay? But you'll see, like for some of the rubbery materials, you don't just trust what's going on really low. They actually will tell you this is the elastic modulus at 10% strain, okay, at a very high value, right? There's no way that a metal you're gonna put a solid bar, I should say. I mean, a metal can of course experience effective 10% strain if it's like coiled into a spring, okay? But there's no way that a metal bar, solid bar, is going to experience that and not have yielded. Okay, so let's do an example. Someone hands you a test sample. The length is 10 centimeters and the diameter is 1 centimeter. We take a measurement in the elastic regime, and the measured force is 10 kilonewtons. The measured extension is 60 microns. What is the elastic modulus? Okay, so we didn't have to build the machine and do all those details, work out all those details here, right? We just have a few numbers that we need to calculate the elastic modulus. So let's start with, well, why don't I calculate the stress, right? So sigma equals E epsilon, okay? So they told us what a force was in the elastic regime. They told us that the diameter was 1 centimeter, right? So we can calculate out force divided by area. Sigma equals E epsilon. How many times are we going to say this? A lot of times this semester. Okay. So how do we calculate out epsilon? Epsilon is the length that we've had in extension, so that's 60 microns, divided by the initial length. That's the 10 centimeters. Okay, so we can figure out what the epsilon is. So E is equal to sigma over epsilon, right? Sigma was equal to E epsilon, so we need to figure out what E is equal to. So we go through this. Area is pi d squared over 4. It comes out to be this. The end result, right? So we had, this is the epsilon going right into here, right? This is the sigma going right into here, and this is what you get. And then, if you write it all out and you're careful with the dimensional analysis, which I understand it's frustrating, okay? And it takes a little bit of space, okay? But 10 kilonewtons is, 1,000 or 10,000 newtons. Centimeter, right, is 0.01 meters. All these things, and like if you have a square, sometimes it's easier to keep it in the square. So do the 1 centimeter, right? Do that conversion inside and then square the whole thing. A micron, right, is 1 10 to the minus 6 meters. All right, so that's these things. And then also, typically, what you're looking at is the elastic modulus given in gigapascals. So first, we converted everything to newtons per meter squared, and then we're going to essentially multiply by 1e to the, or 10 to the minus 9, or divide by 10 to the minus 9 to get it in gigapascals. Okay. So when we do that, we get about 212 gigapascals. Any questions on that? Nice, straightforward. Okay. And if you want, you can look on the IPython code that's included with this session, and you get that result. So what I did it first. This is like code speak, right? Kind of like, okay, I'm first going to calculate out sigma, going to calculate out strain. And then I'm just going to do sigma divided by strain, right? But if you want to just jump right to the whole shebang, right? You write this out on your formula sheet or on your piece of paper, then you can just use IPython as a calculator. It doesn't matter, right? Either way. But this lacks the variables, okay? So it's not as convenient as just being able to change the variables, the values here, and be able to change them. Okay, so look at this chart. This is craziness, but it's fun. Okay, so these are materials, Young's moduli in gigapascals and mega psi. Okay, and they're sorted except for this one because it has greater than, okay, which I guess means it gets down at the very bottom. Okay, they're sorted they're in ascending order. All right, and you can look at the web page. This is a Wikipedia page, and from what I can tell, these numbers look pretty reasonable and pretty accurate. Okay, so here is steel. This is a 200 gigapascals. Okay, 210, 200. That's what I would use for steel. One of the interesting things about steel is even when you alloy it, so you have iron and carbon and some other stuff in it, they pretty much all have the same elastic modulus. So strength could change quite a bit, quite drastically. In fact, we talked about that the last time. We said it could go like from 10 to 700 megapascals for strength. Okay, but the elastic modulus is going to stay the same. If you break this down, I highlighted some of the ones that I think are kind of good to know. Steel at 200 gigapascals, aluminum at about 70. You can't see that, but that's a 68. Titanium, okay, yeah, there might be some problems. That's around 120. Okay, 116 is what that is, gigapascals. Wood, it's around 10 gigapascals. And then the thermoplastics, okay, which are being highlighted here, you can say that they're on the order of a gigapascal. Okay, so you've got a lot of range for the elastic moduli, but it's only 3 orders of magnitude, or 2 orders of magnitude, really. Actually, you get less. You can get less than 1 gigapascal. Okay, but if I give you a resistor, right? I just pull out the resistor in my kit, and I'm like, oh, is this mega ohm or is this like 1 ohm? That's 6 orders of magnitude that the electrical engineers have. Okay, for elastic moduli and stiffness, we don't have that much variability, and the materials can be quite different. Okay. Oh yeah, and the rubbery materials, which I like, that is 0.01 to 0.1 gigapascals. So these are some of the elastic moduli to remember. Steel, it's around 200 to 210 gigapascals. I made an agreement. So if you look, don't worry. On last semester, they wanted a hint on the final. So I said, okay, on the final, question 1A will be, what is the elastic modulus of aluminum? All right, I just told them. All right, they got a point. Okay, 70 gigapascals. The typical rule of thumb is that the elastic modulus of steel is 3 times that of aluminum. That's just the rule of thumb. Okay, but I guess you could just remember both of them. It doesn't really matter. Okay, titanium, like we said, 120. Wood, around 10. Thermoplastics, around 1. And rubber's a fraction of that. In gigapascals, 10 to the 9. 1 gigapascal is 1,000 megapascals. Okay, so these are some to remember. Now, let's go back to that example we did. I think this was the second. Yeah, it was the second time we met, where we said, or maybe it's the third time. No, it's the third time because we did bars as springs. Yes, the third time. So here's a 2,700 pound force pulling this bar apart. And we said that it had a little bit of deflection, 73 microns. Okay. Now let's ask ourselves some other questions. How much strain will the bar experience? How much stress will the bar experience? What is the elastic modulus of the bar? Okay. So strain, that's going to be essentially how much displacement we have over the initial length. So we can do this all out, right? That's the 73 microns, and we said that the length of the bar was 10 centimeters, even back then. So the strain ends up being 0.073%. Stress, well, that's going to be force divided by area. Okay, so we have 12 kilonewtons of force. I take the area as being pi d squared over 4. And we make sure we convert appropriately. We get all into newtons per meter squared. And then we multiply by 10 to the 6, or divide by 10 to the 6 to get in megapascals. So elastic moduli are often in gigapascals, right? You're starting to see this because you have, but then we have these really small strains. Like this is representative value. This is for some steels that will break some steels. Okay, 153, but that's not unreasonable to find a steel that has a yield strength greater than 150 megapascals. So yeah, what I was saying is the stresses are often in megapascals. And elastic moduli are often in gigapascals. So the elastic modulus, right, is going to be given by sigma over epsilon. And so we've now calculated out epsilon right here. We've calculated out sigma, and we get 210 gigapascals. Is that a coincidence? No. I tried. I'm not perfect, but I tried to design the problem to use a realistic K. Okay? So now let's ask the question, wait, we have these Ks. This is Hooke's law. But we now have another form of Hooke's law. How do we relate geometry, elastic modulus, and the bar to each other? Okay, so remember, we spent a whole session looking at This is the K for the bar. And people are like, where did this K value come from? We're about to show you. It comes right here. We have Hooke's law. Oh, I guess we should maybe say that, all right, there's a K, there's an E, right? So K was what we said in terms of kilonewtons per millimeter, right? That's the spring constant, force equals K delta. E is the elastic modulus. Delta is how much this bar extends. L is its length, initial length. And F is the force. Area is the cross-sectional area. Or A is the cross-sectional area. Okay, so the two forms of Hooke's law are sigma equals E epsilon and F equals K delta. The stress is just sigma equals F over A. The strain is going to be the delta over the L. Let's essentially just do some algebra and combine some things with each other. So here we can write a new expression, right, where we have sigma is equal to E epsilon, so plug in F over A on this side, and plug in epsilon, which is right here, the delta over L. And now we have the E. Let's say one of our goals could be to try to solve for the E, or maybe our goal is to solve for a K. Let's do looking at E here, right, and then drop it over into figuring out what's happening with the K, right? Because remember, we had this idea of something newtons per meter for a spring constant. So we put these in here, right? So we have E. We see that I've got this L over delta. Well, I've got this, F over delta, right? And I've got an F and a delta. And so now I can pop in a K here. So E equals KL over A. And we rearrange things, and we get that the K is equal to EA over L. This is one to write down. Now, what does this tell us, right? We like to think about scaling. This is not the scaling relationship that we had for how much load can a bar support, okay? We will do that. We can do that one real quickly now, actually, because we know that sigma is equal to F over A, all right? Do you remember that? So sigma is equal to F over A, and we say, hey, there are yield strengths. There are maximum yields or maximum stresses you can get to. So constant equals force divided by area, right? And we said, hey, the supportable load that this bar can support is proportional to the area, right? So if I increase the area, I can support more force. Okay, that's the stress. Here, what we're talking about is stiffness, right? So how much displacement do we get when we apply a given load, all right? Or how much force do we get, all right? Probably better said because it's K delta. So look, if you use a material that has a higher elastic modulus, you have a stiffer bar. If we increase the cross-sectional area, we have a stiffer bar. And then you remember, springs in series, what happens? Well, you get decreases in the Ks. Remember, we said if you double the length of the spring, you're going to half the elastic constant, or the spring rate, the spring constant, okay? So now we have a relationship based on what we know from Hooke's law in its two forms, and stress and strain. So we can calculate what the Ks are. So it's no longer a mystery. Now, if I have an indeterminate problem, is it easier or harder, right, to think, oh, I have essentially three more terms. I have EA over L, or I just think in terms of Ks and stiffnesses? I think in many cases it's easier to think in terms of the Ks. Okay, so you do the problem in Ks, and then eventually you can plug in EA over L or figure it out, depending on what you need to figure out. Now, another relationship, this is also to be written on your formula sheet, and this is a famous one. Delta is equal to phi, okay? Or I often say pli, okay, PL over EA. So this is a relationship that tells us how much stretch, right? How much change in length we're going to have, how much extension we're going to have for a given amount of force. If I increase the force, I get more extension. If I increase the length, I get more extension. If I increase the elastic modulus, I get less extension. If I increase the cross-sectional area, I get less extension. Okay? Again, these are all kind of intuitive scaling relationships that we've discussed in some way, I guess, when we were talking about springs and series and parallel. But now we have concrete equations that allow us to think about what those values would be for a bar. Any questions? Okay. So let's look at an example with indeterminate loading. Okay, this is the same one. This is back from session 3, okay, where we were using the K's, and we said, hey, the internal load in this member is proportional to the stiffness in that member. So if this is a very stiff member, that means that this internal load is going to be quite high. Okay, so we get K1 over K1 plus K2. This ratio would be close to 1, and it's close to what this force is being applied in the middle. Okay, and the same thing was true for this force here. Notice these arrows are in opposite direction. Opposite directions. This region is in tension or compression, assuming F is positive. Tension, right? And then this region, right, is in compression, right? It's being compressed. So these signs are all correct for the forces. They're both positive forces, but they are in opposite, they're doing opposite things. The behaviors, the material is experiencing compression in one case and tension in the other. So if we want stress and strain in these sections of the bar between the fixed walls, we can't do it unless we have a little bit more information. Okay? Like, I can't tell you, if you don't tell me what the cross-sectional area is here, I can't tell you, okay, what the stress is going to be. Okay. But if I told you the length, all right, and I told you what the material was, all right, so if I know the length of this section and I know the resulting delta because I know the elastic modulus, and I know that length, and I know that strain, and I can then relate it to stress because I know that sigma is equal to E epsilon, right? I don't know how many times I've said it, but that it gets said again. Okay, so let's say, what are we going to give us? What are we work with? Let's say that we're given the diameter, okay? And let's say that the material for both sections is steel with an elastic modulus of 200 gigapascals. Okay, so now we have a little bit more information. We have something about the geometry, right? Before we had essentially nothing besides that there were K's here, and that these were between two walls. We didn't know their length, we didn't know their cross-sectional area, and we didn't know the material either. So, if we know the diameter, right, we can figure out what the cross-sectional area is, and we can figure out what the stress is. Okay. So this is taking F over A, right, pi d squared over 4. Now, did I do this right, or did I make a boo-boo? Sigma 2 is equal to 4F2 over pi d squared. This is where we should be careful. Okay. We might want to put a negative there. Okay. We do want to put a negative because that's a compressive stress. Okay. Our lengths can be calculated from using our formula, right? We said that K is EA over L. So now we can say that L is EA over K. So we can calculate the initial lengths Okay, because they told us what the K's. We were given K's, right? They're here, 200 kilonewtons per millimeter, or 200 times 10 to the 6 newtons per meter. That's really small. And so we can figure out the initial lengths. We can also figure out the strains. And strain can come from Hooke's law in terms of sigma is equal to E epsilon, okay? Or in this case, epsilon is equal to sigma over E. For both of these. And should I be careful? Yes, I should be careful and add a negative. Okay, here. Or, I mean, this is a little bit tricky because if sigma 2 is negative, all right, so I might take this one out here, okay? And this is where kind of having a sense, right? Because if sigma 2 is negative, that means that the strain is going to end up being negative automatically, okay? So sometimes when you do these problems, you'd be like, is it going to be negative or positive, okay? And sometimes it depends on which way you're defining the arrows, okay, coming out of it. Okay, so that's how we go about solving those. All right, how much time do I have? I don't have much time. I just wanted to do a couple things. Okay. Yes. Okay, let's do this, and then we'll talk about something else the next time. No, let's do this, and then we'll talk about something else the next time. All right, so. Okay. Those are axes for a stress strain curve. This is a stress strain response. Let's say that, I don't know, this value up here is 100 megapascals. Let's say this value down here is like 75 megapascals. All right, so like this is kind of coming across like there. Let's say that this value right here is 0.1%. I'm going to copy this because I want to do a couple different things. So in the first case, let's say that we load past sigma y. All right. So where is sigma y? Well, sigma y is here. All right. Let's just say I don't know what it is. Let's say sigma y is equal to 90 megapascals. So we go up, we go up, we go up. Let's say that we actually get all the way and we get to 100 megapascals. So we end up getting all the way up to this point right here. If I had stayed below the proportional limit, below the elastic limit, all right, if I had stayed in this region, okay, I would have just gone right back down, okay, to 0, 0, okay? Would have sprung back, no problem, right? If I'm a muscle or something, you know, I'm just like, I am just doing this over and over again. But let's say that like my buddy decides that it can handle a little bit more weight, right? And I get pushed to have more stress applied to my muscles. Okay? So then I get up to this level and it hurts. And what happens when I drop the weight? Do I get to spring back to 0, 0? I don't. But where do I go? Where do you go, right? Well, for the materials we're dealing with, what we assume is that the slope, right? Remember, this has a slope of E here. You follow the same slope. I want to use a color that's a good color. We're going to follow the same slope back down. Okay? And this is referred to as residual. Whoops. Strain. Okay? So you go up beyond the elastic limit, beyond the yield strength, beyond the yield stress, beyond the proportional limit, whatever you want to call it. And then you release the load, you actually come back down with the same slope. It has the same slope, elastic modulus. Okay. Color, sure, blue. Right? That's, I don't know, whatever. That's not really 1. Okay, it's not 1. All right, but you get the idea, right? That's going to be the slope. So that is a way to predict how much kind of permanent deformation you've put into your system. Now, the other cool thing, I'm running out of time. The other cool thing is you've actually made the material stronger. Okay, this is a wild thing. Now, I added strain. It came at a cost, right? It came at a cost. But you've introduced maybe some dislocations into the material if it's a metal alloy. And so guess what? This line becomes the new linear region. Okay? Here, and actually it goes this way as well. Okay? To here. Okay? So the material will behave, it will go up and down this new linear region with the same slope it had before without yielding until you get there. Once you get there, it will start to yield again. Okay? So like you could keep doing this, right? You could keep doing this. You could like come out here and then you'd get a little bit more strength. Okay? It has a limit, of course. Because if you go past the ultimate tensile strength, you will have caused a significant change in the cross-sectional area, and the material will no longer be getting stronger. Okay? So this is a cool thing that with steels. Now, let's say that you don't know where the yield strength is. Let's say we do not know the yield strength. But you're given the stress strain curve. What you do, okay, is you apply this general rule. It's called the 0.2% offset rule. Okay, or method. So we say, 0.2%, let me pick a different color. Let's do that purple. Okay, so this is 0.1%. This is exaggerated, but this would be 0.2%. Okay, this one right there. So then what you do is you draw a line parallel. Okay, this is a bad example because it shouldn't go past. All right, that's too much. All right, I should have tempered it a little bit. Okay, let's cheat. Let's say that this is let's cheat. All right, I know you're like, why do you do this to me, dudes? Let's say this is 0.15% here now, right there, and that this right here is the 0.2%. Okay, and it goes something like that. All right. Again, that's not the greatest. All right, not the greatest. But you draw this with a slope of e. Okay, and then this value right here becomes your estimate for the yield strength. All right, we better stop there. Thank you guys. Thank you for letting me know that the audio was not working. I think it worked throughout, so we got a little bit of a later start. And we'll pick up discussing more about material properties on Friday. There's an in-class session assignment due tonight, and there is another one that's going to be due on Friday before class. Great. Hold on one second. Yeah, we're going ahead and we're going to stop this stuff.